Dear students, let us we study today about the topic silicates. Silicates are the metal derivatives of silicic acid. Formula of silicic acid is H4SiO4. So the structure of silicic acid is the silicon is connected to 4 OH groups. Silicates can be prepared by fusing metal oxides or metal carbonates with sand. Sodium carbonate, when it is fused with the sand, we get sodium silicate Na4SiO4, which further polymerizes to give Na2SiO3 n times. Some silicates of alkali metals are soluble in water while others are insoluble. The insolubility is due to the great strength of SiO bond. SiO bond is broken when silicates are treated with hydrofluoric acid. Since glass is a silicate, therefore glass is soluble in hydrofluoric acid. So in general, the silicates means they are all the minerals present in the earth crust. The stones, granites, we have varieties of granites. So these granites are nothing but the metal silicates. We also get gems, a very costly gems. They are also a subtype of the silicates. And all these silicates have a single silicate anion called SiO4 4 minus. Now let us we study what would be the structure of SiO4 4 minus. In silicate ion, the central atom is silicon, its atomic number is 14 and electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p2. This electronic configuration shows that the silicon atom contains the 4 electrons in the valence shell. Out of the 4, 2 are present in 3s and 2 unpaired are present in 3px and 3py. When oxygen atom comes nearer to the silicon atom gets excited and one of the electron in 3s shifts to 3pz. Therefore, excited state of the electronic configuration of silicon is 3s1, 3px1, 3py1 and 3pz1, which shows silicon atom contains 4 unpaired electrons. These atomic orbitals undergoes hybridization to form the sp3 hybridization resulting tetrahedral geometry. In this, the silicon atom, the oxygen atom combines with the silicon to form a covalent bond between the silicon and oxygen, and one electron excess in oxygen remains on the silicon because oxygen atom contains the 2 unpaired electrons. This results the structure of silicate as the tetrahedral geometry with a bond angle 109 degree 28 minutes. Silicates differ from one another in the manner in which these anions are linked together. Based on the linkage, the silicates are classified into the 6 types. One is orthosilicates, second pyrosilicates, third cyclic or ring silicates, fourth chain silicates, fifth two-dimensional sheet silicates, and sixth three-dimensional silicates. In orthosilicates, SiO4 4 minus anion is linked to some of the metal ions. So all the 4 oxygen atoms are free. In case of pyrosilicates, out of the 4 oxygen atoms linked, one of the oxygen atom is utilized for the linking to another silicate ion. In case of cyclic or ring silicates and the chain silicates, 2 of the oxygens of silicate ions are used. In case of two-dimensional sheet silicates, 3 oxygen atoms of silicates are used, and in case of three-dimensional silicates, all the 4 oxygen atoms of the silicates are used. Now let us discuss these types one by one. Orthosilicates. These silicates contain the discrete SiO4 4- tetrahedral anions. The oxygen atoms of each silicate anion is also coordinated to the metal ion to impart electrical neutrality to the structure. And all these silicates are, as I have said, they are all the minerals. Now, the examples of orthosilicates are number 1, phenacite. Phenacite is nothing but it is beryllium silicate, formula Be2SiO4, because silicate valency -4, beryllium valency +2. Since 2 beryllium are there, +2 into 2 is +4, -4, total charge 0, hence the formula is right. Similarly, the willemite and olivine also are nothing but zinc silicate and magnesium silicates. Zircon is another orthosilicate, formula ZrSiO4, because the zirconium valency is +4, silicate valency -4, hence the total charge becomes 0. The other examples of orthosilicates are garnets. Garnets are a group of silicate materials used as gemstones and abrasives. All species of garnets possesses similar physical properties and crystal forms, but differ in chemical composition. Examples of garnets are alamandine, euvorotite, pyrope, andradite, etc. In garnets, silicate tetrahedra are arranged about the M2+ ion and M3+ ion, so they become 8 and 6 coordinated respectively. The examples of the garnet, another of this type, is alamandine. Alamandine formula Fe3Al2SiO4 trans. In this case, 3 silicate ions are attached to ferrous and aluminium ions. Each silicate carries -4 charge. 3 silicates means totally it is -12. Aluminium valency +3, +3 into 2 is +6. Similarly, Fe valency is +2, 3 Fe, +2 into 3 +6, +6 +6 +12, and silicate -12. The charge is balanced and the mineral formula is right. This is how you must able to write and remember the formulas of various silicates. Coming to the another silicate called the pyrosilicates. These silicates contain a discrete Si2O7 having 6- charge is. The anion of this is formed by joining 2 silicate tetrahedral units through 1 oxygen atom. And the structure I have shown there, where 2 silicon are attached to oxygen and this oxygen atom is a neutral and it is not carrying any charge. So therefore the outside, how many oxygen are there? 6 oxygen are there, and these 6 oxygens, they have a -1 charge. Therefore total charge is -6, and the formula is Si2O7 having 6 minus charge. Examples of this is, the examples of the pyrosilicates is thoratavitite. Thoratavitite is nothing but it is the scandium pyrosilicate. The scandium pyrosilicate is the Sc2 Si2O7 because the scandium valency is +3. Similarly, hemimorphite. Hemimorphite is a zinc pyrosilicate. Zinc hydroxide and water molecule, they are all present in the water of crystallization of this compound. So the formula becomes Zn3 Si2O7 point zinc hydroxide ZnOH twice point H2O. Coming to the third type of a silicate called the cyclic or ring silicates. Such silicates contain the ring anions like Si3O9 having 6 minus charge or Si6O18 having 12 minus charge. These anions are obtained when each silicate tetrahedra unit shares on oxygen with each of the two neighboring SiO4 units. As I have earlierly said, the ring silicates here, the 2 oxygen atoms are utilized in the formation of a chain with other silicates. Now, I have shown the structure below. Si3O9 is having the 6 minus charge and how this 6 minus charge comes. The diagram shows the 6 minus charges are there in the diagram. Similarly, in the diagram, Si6O18 carries -12 charge. So the diagram also have -12. This means in Si3O9, 3 oxygen atoms are used for linking the 3 silicate tetrahedra. So out of the 9, therefore since 3 are utilized, therefore having the charge 6 minus. Similarly in Si6O18, charge is -12. So 18 minus 12 will be 6. Therefore 6 oxygen atoms are utilized in the formation of a chain. Therefore the charge becomes 12 minus. Examples of this type are benitoite. Benitoite is a barium titanium cyclic silicate. So barium titanium cyclic silicate, here titanium valency is +4, barium valency is +2, +4 +2 +6 -6, total charge becomes 0. The another example is wollastonite. So wollastonite is calcium cyclic silicate. So in this, the formula becomes Ca3Si3O9. And the third is cataplite. So the cataplite is the sodium zirconium cyclic silicate. The cyclic silicates with Si6O18 12 minus anion is beryl. So beryl is nothing but it is beryllium aluminium, the cyclic silicate. Now here the Si6O18 is having 12 minus charge. That 12 minus charge is balanced by 2 aluminium, that is +6, and beryllium valency +2 into 3 +6. So these are all the various minerals of the cyclic silicates. Now this shows what is the structure of the silicate. The silicate structure I have shown SiO4 4 minus. The bond angle is 109.5 degree and the bond length between silicon and oxygen is 162 picometer. In case of pyrosilicates, I have shown the two silicate ions are linked with each other through oxygen, and here the other oxygen is having the minus charge. So totally the 6 minus charge are there. Hence it is Si2O7 carrying 6 minus charge. Below the cyclic silicates, the diagram also have shown, and you must able to draw these diagrams properly. Now here in this I have shown they are all the minerals, the orthosilicates, how it looks. So the example is willemite. So willemite is a stone. Zircon, it is also a type of a stone, and a granite. So olivine gem. So the gems are very costly materials. So it is a perfect crystalline the compound. And similarly almandine is also a gem. So these are all the silicates. So orthosilicates, they are much costlier one. Coming to the pyrosilicates, the example I have shown here, thortivitite, it's a stone. The thortivitite is a stone. Similarly hemimorphite is also a type of a stone, and when you cut you get the pieces like a granites, which you can keep it on your house. Now coming to the third one, that is a cyclic silicates. The cyclic silicates, here the examples are benitoite. Benitoite is a cyclic silicate, how it looks, and also wollastonite is a stone. Cataplite, it looks like this, and the beryl is also a cyclic silicate having Si6O18. Now coming to the other types, called the chain silicates. Such silicates contain the anions which are formed by the sharing of two oxygen atom by each tetrahedron, and the anions may be any one of the following type. The like cyclic silicates, these are the chain silicates. Here also the two oxygen atoms of the silicate is used in the formation of a chain. Now the first one, I have shown the diagram SiO3 n times, and its charge is 2n minus. Suppose if n is 1, we have SiO3. So in this SiO3, so the two oxygen atoms are used for the chain formation, and only the remaining 2 is left, and that 2 oxygen carries the minus charge. Hence SiO3 is having 2 minus charge. Similarly, if I take Si4O11, the diagram I have shown. So Si4O11, if n is equal to 1, then you find there the 6 oxygen atoms, they contain the minus charge, whereas the other oxygen atoms are used in the formation of a chain. Therefore, its structure becomes Si4O11 carrying 6 charge. The silicates having SiO3, the chains or anions, are called pyroxene minerals. So the examples of the pyroxene minerals are spodumene. Spodumene is nothing but it is lithium aluminium pyroxene silicate. Diopside, it is calcium magnesium pyroxene silicate. Similarly, enstatite, it is a magnesium silicate. Its formula is MgSiO3 twice. So MgSiO3 twice is enstatite, and it is also an example of pyroxene minerals. Some synthetic silicates have also been done, and these synthetic silicates examples are lithium silicate, formula Li2SiO3, and sodium silicate, it is Na2SiO3. The silicates having Si4O11 anions have a double chains and are called amphibole minerals. These minerals also contain some OH groups which are attached to the cations. Example for this type is tremolite. So the tremolite is nothing but it is calcium magnesium amphibole silicates. And these calcium magnesium amphibole silicates are having this formula. In this, Si4O11 carries the 6 minus charge. So therefore 2 are there, 12 minus, 2 OH groups are there, totally 14 minus charge. Here calcium valency is plus 2 into 2 is plus 4. Magnesium valency is plus 2 into 5 is plus 10. Plus 10 plus 4 is plus 14. Minus 14. The charge becomes the 0, and this is a neutral mineral. Asbestos minerals also include this category. Now coming to the fifth category called the two-dimensional sheet silicates. When 3 oxygen atoms of each silicate tetrahedra are shared with adjacent silicate tetrahedra, an infinite two-dimensional sheet structures of the composition Si2O5 n times having a charge 2n minus results. The metal ions present hold the layers together by the weak electrostatic forces. As a result, the minerals containing Si2O5 n times 2n minus are soft and cleave easily. Here I have shown in the diagram. So it is having the 2 silicon atoms, they are linked like this, and among the 4 oxygen, 3 oxygens are utilized for the formation of a chain. So therefore each silicate ion is left with 1 oxygen having a minus charge. Therefore here 2 silicates are linked, hence the charge becomes the 2 minus. Now the micas and different types of clay minerals are the examples of this category. The clay minerals like talc. The talc is nothing but it is the magnesium, the sheet silicate. The magnesium sheet silicate, the formula is Mg2Si2O5 twice MgOH twice. It contains magnesium hydroxide. It is together it will be the talc. If you make a fine powder, this powder is used. Is used in the preparation of some synthetic powders with some smell. And kaolin is another example of this type. The example, the kaolin formula is Al2Si2O5 OH 4 times are the examples of the clay materials. Now coming to the last type, that is 3-dimensional silicates. In this, when all the 4 oxygen atoms of the silicate tetrahedron are shared with adjacent tetrahedra and the process is repeated, an infinite 3-dimensional structure results. Since all the oxygens are the bridge atoms, the silicate is neutral because that silicate ion is not having any charge. If Si4 plus is not replaced by the metal ions, the silicate is neutral, having the formula SiO2. The examples of this category is the quartz, tridymite and cristobalite are the examples of this type. If silicon 4 plus is replaced by aluminium 3 plus ions in the tetrahedral positions in the SiO2 structure, in order to maintain electrical neutrality, some other monovalent cations must be introduced. Because you know the silicon valency is 4 plus, but to make that 4 plus, because aluminium valency is 3 plus, so to make 4 plus, the monovalent cations like Na plus and K plus are introduced in this three-dimensional silicates. Minerals like feldspar, zeolites and ultramarines are the examples of this kind of three-dimensional silicates. Here I have shown a chain silicates, how the chain silicates looks. The students, you must practice to draw these structures. Now in the chain silicates, you have single chain silicate and also have shown the double chain silicates. These double chain silicates are also called amphibole silicates. Now, this is an example of the sheet silicates, how the sheet silicates it looks. Here I have shown some of the minerals and how they look. Now, these are the minerals, the chain silicates, they are the pyroxene minerals and amphibole minerals. The pyroxene minerals like spodumene, it is a granite, a diopside, enstatite and the tremolite. So these are the chain silicates. These are the two-dimensional sheet silicates. The two-dimensional sheet silicates like mica, the talc and kaolin, these are the two-dimensional sheet silicates, how they look. And the three-dimensional silicates are the quartz, then the cristobalite, these the silicates, and the other and the three-dimensional sheet silicates are the feldspar, zeolite and ultramarine. So in these cases, so the silicon 4 plus is replaced by the aluminium ion and the sodium and some the potassium ions. So this shows the how the silicates, they are a solid crystalline the silicates like granites, and also you have the clay, and also you have some of the gems, they belongs to the class of this category. The students, so try to learn once again and remember the names of the minerals that are present in the types of silicates with the chemical formula. Thank you.